Okay, so Arrhenius was fairly early on, knew that there's a problem with his definition, and the problem centers around ammonia. Because ammonia doesn't contain any hydroxide ions, but yet when you dissolve the ammonia up in water, you get an increase in the concentration of hydroxide ion. So, where does this hydroxide ion concentration come from? Why is ammonia creating a basic solution? We need a new definition. Okay, so we're ready to move into our second definition for acids and bases. And our second definition is the Bronsted-Lowry definition. Now, it's named after two different scientists who essentially came up with the same idea and published it in different journals at the same time. And there was fights over it for years and years about who was going to get credit, and they just ended up giving them both credit. Now, I put the 1923 up there because that's the year this definition emerges. Okay? No, that's not going to be on the test. So, under the Bronsted-Lowry definition, which, by the way, guys, is the most commonly used definition for acids and bases, an acid is a species that can donate a hydrogen ion. So we talk about acids being proton donors. This isn't really a change from the Arrhenius definition, because all Arrhenius acids are hydrogen ion donators to water to create the hydronium ion. So HCl is a proton donor. But also something like H2PO4 1- can be a proton donor. Bases, here's where the big change comes, is any substance that can accept a hydrogen ions. So bases are proton acceptors. And in the Bronsted-Lowry then definition, an acid-base reaction is a hydrogen ion exchange or transfer. Okay? So a base, to be a proton acceptor, a hydrogen ion acceptor, has to have a lone pair of electrons. And this is the major change from the Arrhenius definition. So the hydroxide ion itself, once it's released into water, is a proton acceptor, a hydrogen ion acceptor, because it has 3 lone pairs of electrons on the oxygen. Okay? And if we look at ammonia, we can see that ammonia has a lone pair of electrons on the nitrogen. And remember, nitrogen is a fairly small atom, it's fairly electronegative, and so that it can have a strong attraction for an electron, a hydrogen-starved atom. Okay, and it can pull that nucleus, essentially the proton, away. So the ammonia can act as a hydrogen ion acceptor. This also means anions, like the fluoride ion or the nitrite ion or the acetate ion can also act as hydrogen ion acceptors. So you no longer have to contain just a hydroxide ion to be a base. This is the real expansion here of our definition. Okay? So the Bronsted-Lowry definition centers around a hydrogen ion exchange. So let's look at these two reactions. HF plus water going to hydronium ion in the fluoride ion. Okay? HF goes to the fluoride ion. So moving from reactant side to product side, HF donates a hydrogen ion to water to give us the hydronium ion and the fluoride ion. So acid, water here is acting as a base, okay, because it accepted. Now, if we think about this reaction running in reverse, because remember it's going to come to dynamic equilibrium, so the reaction is happening in both directions. For the fluoride ion to go back to being HF, the fluoride ion has to accept a hydrogen ion, and the hydronium ion has to donate. So I have acid, base, acid, base. So in a Bronsted-Lowry acid-base reaction, an acid and base react to create a new acid and a new base. reacts with a base to give me a new acid and a new base. Now, let's look at the second reaction. Ammonia goes to the ammonium ion. Okay? For ammonia to go to the ammonium ion, NH3 to NH4+, it had to accept a hydrogen ion. And where did it get it? It got it from water. Water goes from H2O to OH-. So base, acid, acid, base. Now, one of the things I want you to notice here is that in this top reaction, water is acting like a base. In this bottom reaction, water is acting like an acid. Okay? So, I want you to notice that behavior about water. I also want you to notice that an acid cannot donate its hydrogen if there's not a base there to accept the hydrogen ion. Okay? Water, because it can act as both an acid and a base, is referred to as an amphoteric substance. Any substance that can act as both an acid and a base, accept a proton and donate a proton, is amphoteric. Being small and very polar and having an oxygen, the second most electronegative element on the periodic table, at the center of a water molecule, and having two lone pairs of electrons and two hydrogens attached to the oxygen, makes water incredibly unique, okay, and is one of the reasons why water is amphoteric. Water is so good, though, at being amphoteric that water can undergo autoionization, or what we refer to as self-ionization. Okay? So a water molecule can actually react with a water molecule to give me hydronium ions and hydroxide ions. So water molecule liquid plus water molecule liquid gives me hydronium ions and hydroxide ions. If we write the equilibrium expression for this, we get K equals hydronium ions to hydroxide ions. There's nothing in the denominator because both of those are pure liquids. Okay? This equilibrium expression is called Kw, the self-ionization constant for water. Just Kw. Kw has a value of 1.00 times 10 to the minus 14. And in absolutely positively pure water, hydronium ion concentrations and hydroxide ion concentrations are going to equal each other. Okay, so let's look at an ice chart here for this reaction happening in absolutely positively pure water. So in the beginning, there are no hydronium ions, no hydroxide ions, so it's going to be plus X and plus X on the change line. So I have X and X. In pure water, the concentration of hydronium ions and hydroxide ions equal each other. So therefore, 1 times 10 to the minus 14 equals X times X, or X squared. So X is 1 times 10 to the minus 7. Okay? Look that over. This leads to the following statement. In pure water, hydronium ion concentration equals hydroxide ion concentration, which is 1 times 10 to the minus 7. When we dissolve an acid up in water, we disturb this self-ionization, autoionization reaction. Okay? Le Chatelier's principle is going to come into play here. So we've disturbed the system from equilibrium, we've introduced a stress, an acid or a base. So when we dissolve an acid or a base up in water, we're going to disturb this equilibrium. And the system is going to run in one direction or the other to reestablish the equilibrium. Hint, if I add hydronium ion in or hydroxide in, I cause the self-ionization reaction of water to run backwards to re-achieve an equilibrium. So to determine the hydronium ion and hydroxide ion concentrations in a solution of a strong acid or strong base, we use the original concentration of the strong acid and strong base, and the Kw equation to determine the concentrations. So let's look at a really simple reaction here. Okay? So If we look at dissolving 0.0030 molar, creating a hydrochloric acid solution of 0.00030 molar, then if we look at the moment right after the disturbance, the concentration of hydronium ions is 0.0003 molar. Hydroxide is 1 times 10 to the minus 7. Now, this reaction is going to run in reverse to get back to equilibrium. So it's going to be minus x. So I have 0.0003 minus x and 1 times 10 to the minus 7 minus x. Now, x has to be less than 1 times 10 to the minus 7. So if I subtract it from this hydronium ion concentration, I'm just going to get 0.0003. So if I substitute this in, I get Kw is equal to 0.30 times 1 times 10 to the minus 7 minus x. Okay? Now, I'm really not interested in x so much as I am in hydroxide ion concentration. So if I simplify this down, and I made a typo there, let me fix it. I had a concentration of, 3 zeros. If I did this and I solved for hydroxide ion concentration, because X is going to be very, very tiny, then what I get is hydronium ion concentration. Well, if I solve this, I'm going to solve for hydroxide ion concentration. What I get is hydroxide ion concentration is going to equal let me punch this through on my calculator so we have a number. 1 exp 14 negative divided by 0.00030. I get the hydroxide ion concentration to be 3.3 times 10 raised to the negative 11. Okay, now look at how small that is. That means X is even tinier. So the size of X on that ice chart is so tiny that we're really never going to look for X itself. We're going to look just for the hydroxide ion concentration. So if we simplify this down and just say that Kw always has to equal hydronium ion times hydroxide ion concentration, you can see I get hydroxide is 3 times 10 to the minus 11. Okay? So the hydroxide ion, let's look at the hydroxide ion concentration, and the hydronium ion concentration is 0.0010 molar sodium hydroxide solution. Now, sodium hydroxide is a strong base. So that means that the concentration of hydroxide ions is the same as the original concentration of the salt, 0.01 molar. Hydronium ion concentration then, okay, is going to equal Kw divided by hydroxide ion concentration. So 1 times 10 to the minus 14 divided by 0.001, I get 1 times 10 to the minus 11. So let's try a few, okay? let's come over here and let's play on the board. Let me grab some things here. So let's say I have a concentration of HCl equal to 0.25 molar. I know that Kw equals hydronium ion concentration times hydroxide ion concentration. And in this situation, the concentration of hydronium ions is going to equal 0.25 molar because this is a strong acid. And for right now, we're only dealing with strong acids. Okay? So if I want to get the hydroxide ion concentration, okay, then I'm going to rearrange things and say that hydroxide ion concentration equals Kw divided by hydronium ion concentration. So hydroxide ion concentration is 1.000 times 10 to the minus 14 all over 0.25 molar. So I'm going to divide this out. 1 exp 14 negative divided by 0.25. So I get a concentration here of 4.0 times 10 to the minus 14. Okay. Now, what if I had a concentration of potassium hydroxide of 0.067 molar? Okay, potassium hydroxide is a strong base. That means that the hydroxide ion concentration here is 0.067 molar. So now I'm going to calculate hydronium ion concentration. Hydronium ion concentration is just going to be Kw divided by hydroxide ion concentration. So hydronium ion concentration is 1.000 times 10 to the minus 14 divided by 0.067. One exp 14 negative divided by 0.067, and I get 1.5 times 10 to the minus 13. Okay, now one of the things I want you guys to notice here is that even in a strong base solution, there are some hydronium ions. Not very many, but there are some. If you look back at the last example, in the strong acid solution, there were some hydroxide ions. Okay? So we've tried a couple. There's going to be some in your homework for you guys to do. So just a reminder, I've embedded in your notes that given the concentration of a strong acid, and we want to find the concentration of hydroxide ions in solution, the hydronium ion concentration equals the concentration of the strong acid initially, and hydroxide ion concentration is going to be 1.00 times 10 to the minus 14 divided by hydronium ion concentration. Given a strong base, and we want to find the concentration of hydronium ions, it's just hydronium ion concentration is equal to 1 times 10 to the minus 14 over hydroxide ion concentration, where the hydroxide ion concentration equals the concentration of the strong base to begin with. Okay? So you can look at practice problem 16.2 on page 697 in your book to get some more practice. Now, Since we have both hydronium ions and hydroxide ions in solutions of acids and bases, we need to now define what we mean by something being an acidic solution and something being a basic solution. Okay? We say a solution is acidic when the hydronium ion concentration is greater than hydroxide ion concentration. We consider a solution to be neutral when hydronium ion concentrations equal hydroxide ion concentrations, and a solution is basic if the hydronium ion concentration is less than the concentration of the hydroxide ions. Now, when we're dealing with hydronium ion concentration, hydroxide ion concentrations in solutions, we're dealing with really small numbers. 1 times 10 to the minus 7, 1 times 10 to the minus 10, 3 times 10 to the minus 12. If you mention numbers like that in the general population, their eyes are going to roll back in their head. If I said, you know, that concentration is 1 times 10 to the minus 13 to my mother, she would look at me like I'd grown horns. Okay? So, a very convenient way to express concentration in a fashion that's much more palatable to Joe generic public and actually allows you to write the concentration in a more compact fashion is to use the P function. Okay? P is a mathematical operator, and P equals taking the negative log of whatever. Got away from me. Okay? Turns out that pH is the negative log of hydronium ion concentration. pOH equals the negative log of hydroxide ion concentration. And for a given solution, pH plus pOH always has to equal 14. Okay? So we're going to look at calculating the pH and the pOH of some different solutions. We're going to look at 0.0020 molar HBr and 0.000, how many zeros do they get? 4. 050 molar KOH. Okay? Now, HBr, this is an acid. I know it's an acid because H is written in front. So I know that the hydronium ion concentration is 0.0020 molar. That means that the pH is going to be the negative log of 0.0020 molar. So let's do that. 0.002 natural log, just log. It gives me a pH of 2.70. Now, the pOH for this solution is just going to be 14.00 minus 2.70 and 11.3. Now, you don't hear pOH nearly as often as you hear pH, okay, but I want you to know both. Now, down here, KOH, this is a base, and it's a strong base. Switch pins, this one's dying on me. Okay, since this is a strong base, I can say the pOH equals the negative log of 0.000050, and I get 4.30. The pH of this solution is then 14.00 minus 4.30, and I get 9.7. if we had absolutely positively pure water, the pH would be the negative log of 1 times 10 to the minus 7, pH of 7. Because remember, look back in your notes, in absolutely positively pure water, the hydronium ion concentration equals the hydroxide ion concentration, which is 1 times 10 to the minus 7. And the pOH here, negative log of 1 times 10 to the minus 7, is again equal to 7. So in pure water, the pH and the pOH are both 7. Okay? Now, we can look at, let's see, let me look at practice problem 16.3 and see if we still want to do that. Let's look at problem 16.4. Well, we'll look at 16.3 and 16.4 both. How's that? Okay. Now, problem 16.3 and 16.4 are both on page 699 in your textbook. We look at problem 16.3, it says calculate. Now let's slide this over. It says calculate the pH of each solution and indicate whether the solution is acidic or basic. All right? So I'm going to write both of those concentrations of things down. So in part A, the concentration of hydronium ions is given to us as 9.5 times 10 to the minus 9. Okay? In part B, we're given a hydroxide ion concentration of 7.1 times 10 to the minus 3. Okay? And it wants us to calculate pH. Now, this one's very easy. pH here is just going to be the negative log 9.5 times 10 to the minus 9. Okay, calculator. 9.5 exp 9 negative. So I get a pH here of 8.02. Okay? Down here, I've got a base. So I'm going to first calculate the pOH. It's going to be the negative log 7.1 times 10 to the minus 3. And I get 2.15. The pH is going to be 14 minus 2.15, which would be 11.85. Now guys, because these concentrations have two significant figures, our pHs and pOHs run 2 places past the decimal. And that's because we're dealing with logs. Okay? Now when I look at both of these solutions, we want to ask the question, how do I know if something's acidic, basic, or neutral? Okay? So let's talk about a chart, and then we're going to come back and look at these numbers. Okay. If we look at this chart, we talk about something being acidic if its pH is less than 7, so that its hydronium ion concentration is going to be greater than 1 times 10 to the minus 7. Okay? If it is neutral, pH is going to equal 7. Hydronium ion concentration is going to equal 1 times 10 to the minus 7. And if it's basic, the pH is going to be greater than 7. The hydronium ion concentration is going to be less than 1 times 10 to the minus 7. Okay, let me fix this real quick. I also gave you the relationships for pOH. We usually really deal with pHs, so I'm not gonna really stress that. So acidic, pH less than 7, neutral, pH equal to 7, a solution we consider to be basic if the pH is greater than 7. So let's look at the solutions here that we were just calculating things for. The pH of our solution here, this 8.02 is greater than 7, so we have a basic solution. Here, this is greater than 7, so we have a basic solution. So both the solutions we were given were basic solutions. Okay? Now, one of the nice things about pH is we have machines that measure pH, and when we write pH, it's in a much more compact way to print. So we ought to be able to go from pH to hydronium ion concentration, and from pOH to hydroxide ion concentration. So when we look here, okay, I want you to notice that hydronium ion concentration is just equal to 10 to the minus pH. Hydroxide ion concentration would just equal 10 to the minus pOH. And we're going to look at problem 16.4. Okay? So if I scroll down here, we look at problem 16.4. Okay, right there in the middle. It says calculate the hydronium ion concentration for a solution that has a pH of 8.37. So we've got a pH equal to 8.37. And we want to know hydronium ion concentration. Okay, so let's play with this. So what I have to say is that the hydronium ion concentration is just going to equal 10 to the minus 8.37. So I'm going to take 8.37, make it negative, and you should have a raise 10 to that power button on your calculator. So I get 4.3 times 10 to the minus 9 molar. Okay. Notice the pH is above 7. The hydronium ion concentration is less than 1 times 10 to the minus 7. Okay. If I now wanted the hydroxide ion concentration in here, there are a couple of ways I could do it. I could go 1 times 10 to the minus 14 divided by 4.3 times 10 to the minus 9, because remember, hydroxide ion concentration in solution equals Kw divided by hydronium ion concentration. One exp 14 negative divided by 4.3 exp 9 negative. And I get a value here of 2.3 times 10 to the minus 6. Okay? So, you should be able to go from pH back to hydronium ion concentration. Let's see, CC, page 700. Let's see if we still want to do this problem. Okay. let's look at the conceptual problem 16.5. It's a reasonable problem. Okay, so if we look at the conceptual problem here, as the pH of a solution increases, gets higher, what happens to the acidity of the solution? So if the pH is increasing, we're getting a larger pH value. That means that the acidity of the solution is decreasing. Low pH, high acidity, high concentration of hydronium ions. Low pH, a higher pH, lower concentration of hydronium ions. Weaker or the less acidic the solution. Okay? Now the other problem that I brought up was problem 53 at the end of the chapter. I don't want to bore you too much as you're watching a video and can't interact with me. So let me see if we really need to do that. No, but it would be one I suggest that you guys try on your own. Now guys, I'm going to stop right here. This is where material for test 2 ends. So when you get done with this video, you're done with test 2.